Hi, this is Richard Gibson. This video continues our series of tutorials providing background to help explain common distributed acoustic sensing or DAS observations of low-frequency signal generated by propagating hydraulic fracture systems. In our previous examples, we started by considering relatively simple scenarios where the treatment well is located at the same depth as the monitor well where the fiber optic cable is installed. The data examples also included fracture hits, where the fracture system intersects that monitor well, generating some very large and complicated signals in the DAS dataset. But many applications represent different geometries and different behavior. Here, I'm showing a data example from a recent publication with a catalog of many different datasets and model simulations. The link where you can find this paper will be included in the description of this video. Though the details of the field setting are not included in the publication, the general situation is that the fracture system propagates either over the monitor well or below it. And here in this schematic, I'm showing the fracture system generated or induced in the blue treatment well passing over that green monitor well. But again, it could pass below it, and the observations will be more or less the same. And the key point is that in this configuration, we see a signal in the red positive value strains as the fracture system approaches that monitor well, which looks more or less like the heart-shaped signal we saw in previous examples. But after the time point where the fracture passes over the monitor well, that time point indicated by the white dashed line here, we see a reversal or a mirror image of that heart-shaped signal generating this bow tie. And we have negative blue-colored strains above and below the bow tie. We're going to show a simulation of the results of such a propagating fracture generated using the same general approach as described in the last video. A few key points regarding the geometry are shown here. The lateral offset between wells is 50 meters. The monitor well is 40 meters below the treatment well. When the fracture passes over the monitor well, the bottom edge will be 20 meters above the monitor, and the fracture propagation speed will be a constant 1 meter per minute, and its height will also be a constant 30 meters. And again, we'll be applying the same quasi-static modeling approach used in the last tutorial video. Here, I'm showing a map view of the computed strains for a fracture which is located directly over the monitor well to help build some intuition. The fracture itself is shown by this short green line here. The red arrows show the sense of motion of each face of the tensile fracture. And we are generating from this fracture these red positive valued strain lobes, which, as the fracture propagates both to the right and to the left, those same positive valued strain lobes will be propagating with that fracture tip. Here, this movie, we show exactly that result. On the left, we have a map view where the treatment well is shown by the blue line at coordinate 0. This is the monitor well shown in green, and this white line is scrolling along to help you track the time corresponding to the map view shown on the left. And I should say that this right illustration here is the prediction of the DAS data set as a function of depth here, or measured depth, or the north-south coordinate along the well, as well as time. In general, we can see that as the fracture tip moves to the right, again, those strain anomalies move with it, so that the result is that we detect a bow tie. These red lobes, which draw closer and closer to each other until the fracture system passes over the monitor well, and then they separate again as time goes on. We can also compare that final result prediction to the data example we started with, noting again that we don't have all the details for the time and distance values in the data set, making it a little bit difficult to match exactly the shape and configuration of the plot. So the shape and the geometry of my predicted bow tie is a little bit different, but we definitely get the general trends correct. We have converging red positive strain lobes, as shown here, which coalesce almost as the fracture process passes over the monitor well and then diverge again, much like we see here in the data set. So to summarize, our quasi-static model helps to reproduce the general observations. As noted in previous tutorials, this is still a relatively simple model, but it can capture the broad trends that we see in the data. In particular, we can reproduce and explain the bow tie signal observed when there is no fracture hit and the fracture system passes over or possibly under the monitor well. In these cases, we avoid the complexity in the data of the huge strain values which are measured during a fracture intersection or hit when with a well equipped with a fiber optic cable. Thanks again for watching. Upcoming tutorials will continue to dive into some of these more complex features and scenarios that we've been mentioning in the course of this video today.